Hello everyone, this is Hunor Csala from University of Utah, working with Amir Arzani. I will be presenting our work on enhancing corrupt cardiovascular flow data with machine learning. I mostly work with computational fluid dynamics data, which is always clean and smooth. However, we all know that real-world data is corrupt. It can be noisy, it can have missing entries, outliers, and other artifacts. Luckily, there's a myriad of machine learning techniques, mostly in the image processing community, that were especially developed for handling corrupt data. Today, I will be focusing on the top two methods, matrix completion, which is the task of filling in missing entries in our data, and denoising, which is the task of separating the signal from the noise. There are a few other methods, like inpainting, where a big chunk of our data is missing and we want to fill that gap in, usually by generative models, super resolution, going from low resolution to high resolution, and outlier detection. Our first test case is an internal carotid artery aneurysm CFD data. It's a 3D unsteady simulation made in Cardiovascular. Here's the geometry. Uh, the aneurysm region was cropped, and we only used that for further modeling. We voxelized our data, practically interpolating to a 3D uniform Cartesian grid. We only used the velocity magnitude. Then we artificially corrupt our data by adding Gaussian noise or deleting random entries. The first method that we will look at is a denoising autoencoder, which we use in a supervised way where we train with pairs of clean and noisy snapshots. So the input is noisy, but in the loss function, the target is clean. We trained this network on 7 simulations with different Reynolds numbers from 360s to 680, each of them having 1000 snapshots, then tested on a Reynolds number that was not included in the training set. The neural network architecture is an autoencoder, where the specialty is that the middle layer has a much smaller dimensionality than the input and the output. This forces the network to learn a meaningful representation of our data. By looking at the videos, we can see that the denoising autoencoder works pretty well, and our output looks quite noise-free. The downside of supervised learning in the previous case is that it needs clean data. However, we might not have access to clean data. There's a technique called noise to noise where there's no need for clean data. And in the loss function for the target, we use a second sample, which is also noisy. So it's the same snapshot, it's just another sample from the same noise distribution. We can see that this also works, and the network can denoise our input without ever seeing clean snapshots. Obviously, the theory only holds for certain noise distributions, like Gaussian, for example. Taking this one step further, uh, another method is called noise to void, where there's no need for clean data or a second noisy sample. We are learning straight from the noisy data. Here, the two main assumptions are that the noise is pixel-wise independent, meaning that from one pixel's noise, we cannot estimate another pixel's noise. However, the signal is not pixel-wise independent, meaning that uh, we can estimate the value of one pixel from its neighbors. How this works in practice is we mask some of the input pixels at random. We feed our snapshot through a UNet, which is a fancy convolutional autoencoder. We get our output and we calculate the loss corresponding uh, only to the masked pixels in the input. Practically, this is a noise-to-noise loss on the masked pixels. At the top, we see the results. So this also manages to get rid of the noise to a pretty good level. A more conventional approach is robust principal and component analysis, where we try to decompose our data matrix X into a sum of two matrices, L and S, where L is a low rank matrix containing the signal, and S is a sparse matrix containing the noise. We can do this to convex optimization. Let's compare the results quantitatively. Here is the relative reconstruction error as a function of noise fraction from 10% to 70%, while keeping the noise level constant at 10%. That's practically the standard deviation of the Gaussian distribution. Overall, we see that robust PCA is great, especially for less noisy data. However, for highly corrupted data, the denoising autoencoder works best, and it has a low dependency on the amount of noisy data. Probably this is because it has been retrained separately on each noise fraction. The next task is low-rank matrix completion. Here, data is missing at uniform random locations in space and time. Here we see an example where we uniformly observe 20% of the data, so 80% is missing. Methods to do this task, some of them are based on iterative low-rank SVD decompositions with thresholding. We can also use probabilistic PCA, which makes an assumption about the latent space. And we can also use deep learning methods. Here are the three SVD-based methods, and we can see that all of them do a pretty good job, even when 80% of our data is missing. Obviously, we can do this using the supervised way where we train with clean and corrupt data pairs, similarly to the noisy case. Using a similar autoencoder architecture, we can see that the network learns to fill in the gaps in the flow field. Let's compare our results. Again, a relative reconstruction error as a function of the fraction missing from 10% to 90% missing. Overall, the SVD-based methods work well, especially for smaller percentage of data missing. Again, the autoencoder is less sensitive for the fraction missing, and for 90%, actually the denoising or like the imputing autoencoder works the best. However, there's a major disadvantage for the SVD-based methods. If our data is not random in space and time, for example, if it's fixed, the location where the data is missing is fixed, the SVD-based methods completely fail, even if a small percentage of the data is missing. What happens here is that this probabilistic PCA algorithm just assigns the mean values to all of the missing entries. However, the neural network-based methods can still work because they are trained on 7 different simulations with different Reynolds numbers. So each of them has a fixed location of missing data, but the fixed location changes for each simulation, so the network can still learn. The next test case is an in vitro 4D flow MRI experimental data from a patient-specific aneurysm model. Here we use all 3 velocity components. You use raw velocities without any post-processing. The denoising methods that we will see are filtering, robust PCA, noise to void, and the denoising autoencoder trained on artificially noisy CFD data. The first step is we want to estimate the noise level in the MRI snapshots. To do this, we have CFD simulations. We add artificial noise to it to get a noisy snapshot. We feed this noisy snapshot into a neural network, and the output is only one single number, which is the noise level. This way, we can teach a network to estimate the noise level from a snapshot. We train this on artificially noisy CFD data, then we can use this to infer the noise level of the 4D flow MRI snapshots. Here we assume the noise is Gaussian, which is not true for a 4D flow MRI noise, but it gives us a reasonable approximation. For a supervised denoising scenario, we need CFD data. So we did a few CFD simulations. To validate the CFD, we have steady PIV results on the right, comparing with steady CFD, and they show good agreement. So we are training on three CFD simulations with three different Reynolds numbers plus artificial noise at the noise level that was inferred from the 4D flow MRI snapshots. Um, we test this method on the in vitro 4D flow MRI data. So that's the input to our network. Then the output is the denoise flow field. Then we can compare it to the ground truth CFD. By ground truth, I mean it's at the same Reynolds number as the 4D flow MRI. Let's compare all of our methods. So left is the ground truth CFD and the raw 4D flow MRI. There's the denoising autoencoder, filtering, noise to void, and robust PCA. What is immediately clear is that robust PCA doesn't produce a smooth result. To compare the results quantitatively, we can compare it to the ground truth CFD. Here we see the absolute error compared to CFD as a function of the time. Overall, robust PCA doesn't work that well for this case, which can be somewhat surprising since it's worked very well for the artificially noisy case. The denoising autoencoder is the best, but it's only slightly better than filtering. Except robust PCA, no, the other methods don't use the temporal information of our data, meaning that practically they act on each snapshot separately. As a conclusion, we've seen some methods to handle noisy or missing data for artificial and experimental cases. Most methods have strong assumptions like randomly missing data, Gaussian noise, which are not necessarily true for real-world fluid flow data. All of these methods have been purely data-driven, so adding physics could help, for example, in enforcing conservation of mass. We've seen a way to mix CFD data with experiments. We trained with clean CFD and artificial noise and tested on true experimental data. Here the question is how to evaluate the results, as the CFD will not match the 4D flow MRI to 100%, even if everything is noise free. Then the other thing I want to mention is that we want to think more about how to use these state-of-the-art denoising methods like noise to void, and other variational autoencoders that are very well developed in the image processing community, and they work very good even in an unsupervised case where we don't have access to clean data, which is mostly the case for us. Thank you for the attention. Here you can find my contact information.